higher derivatives, the second derivative, and beyond. So everything we've been doing so far has been the first derivative. We've just called it the derivative. Right? I don't know, have we used the word first derivative? No. But since it's the first one we did, it is sometimes called the first derivative. And then you have second derivatives and third derivatives and so on and so forth. Are they crazy complicated? No, absolutely not. In fact, all it is doing the derivative again. So if you did the derivative once, that's your first derivative. That shows up as a single dash. Your second derivative has two dashes, or a y with two dashes, y double prime, f double prime. So in our language, with the first derivative, we would say f prime of x. With the second derivative, we'd say f double prime of x. F triple prime of x would be the third derivative. And in Leibniz notation, it's d2y by dx squared. And the reason we have this notation in Leibniz notation is because when you're doing the derivative in Leibniz notation, you know how you had this? Remember I wrote that sort of an implicit differentiation? I said to take the derivative of something, you can say d dx of, and put it in brackets. Now, if you had the d dx of the d dx of something, the result is on the top, the d's would get squared, and on the bottom, the dx would get squared. So technically, if the mathematicians were proper with their notation, they should probably write that dx squared in brackets. But mathematicians don't like brackets and just sort of go, yeah, but I know consistency, sometimes they let it go. It looks like just the x is squared, but technically, d squared y. I bet you there's some places that say d squared y. And notice in the language, though, we say dx squared as if the whole thing is squared. But you wouldn't be able to tell when I say dx squared or dx squared. It's all on hesitation on when you say. But logically, this is what's happening. You're doing the d dx twice, which would make sense that that's why the squared is in between the y and the 2, because you've done the derivative twice with respect to y over dx. Okay, so what does this mean for us? Well, finding the second derivative just means you found the first derivative first. You've got your answer. Usually it's helpful to simplify it a little bit so that when you take the derivative again, you can do the derivative again. So what does this look like for us? Well, same process as before. You're finding a derivative. Your first step is this in a form that I like, or should I rearrange something to make it nicer? In this case, I would probably take the time to rearrange the second one so it's easy to use my power rule. Otherwise, I'd have to use a quotient rule, and the quotient rule is longer and more tedious. Now that I have my derivative in a form that I can do, f prime of x, the 3 would come out in front. The negative 1 would come out in front. Subtract 1 from my exponents, and I have my first derivative. Then my second derivative is just the derivative of the first derivative. Again, just power rules. The 2 would come out in front. Oops. If my negative 2 comes out in front, this would become negative 10. X to the negative 3. Yes. Yes, for sure. Or even, this might even be better up here. Would it be hard to find the third derivative? No. What's going to eventually happen with that first term? It's going to eventually go to 0. Oops, here we go. Third derivative. Now it'll be plus. Right? Is there a pattern happening? Absolutely. Okay? Could we, at a certain point, they just say, like, the 30th derivative of x? Well, which part is going to be easier to figure out? This first part would go to 0. So for sure, it would still be at 0. And then this part will either be positive or negative. Can you see a pattern? Can you tell me if it's going to be positive or negative? Negative. Well, why do you think it's going to be negative? The even ones are negative. The odd ones are going to be positive. And it's going to flip-flop. Good. So it's going to be negative. Excellent. What's going to be the number in front? Big. Can you tell me a way I could write the number in front? Shorter than that, though. Anybody see a short way that I could write the number in front? And we're going to also have an exponent. I think the exponent thing is going to be a little bit easier. Negative 31. Good. There's pattern recognition. Would you agree if I wrote 5 times 30 factorial? Does that make sense? Because the first one, or wait, let's see. This is 5 times 2. And then this one is 5 times 3 times 2. And the next one will be 5 times, because the 5 is there originally, 4 times 3 times 2. And 4 times 3 times 2 times 1 is 4 factorial. And then eventually, following that pattern, at 30, you would still have the 5, and then you would have 30 times 29 times 28 times 27 times 26 times 25, all the way down. Insanely large number, but not too large that your calculator gets mad. Yes, because at a certain point, your calculator gets mad and doesn't like it anymore. Maybe, depending on which calculator you have. Different ones have different powers. I wonder if does the TI-84 give more memory? They do. No, they didn't. I think the TI-84 didn't change how when its numbers run out of problems. Okay. So we get our notation this way. d2y over dx squared if y is this. Yes, I know. But and there's a whole branch of mathematics that you can take that looks at which decimal. I took a course in university which I could find out at what decimal place do we lose our certainty. So, good stuff. So you can actually do calculations on your calculator, and if you continue to do calculations on it, eventually you can get no answers in your answer that are correct, which is disheartening. Okay, so here, if I wanted to find dy dx, if I was looking at this one normally, I would say this looks like a great example of the chain rule. So if I use my chain rule first, I would get a 3 out in front, keep the inside the same, subtract 1 from the exponent, multiply by the derivative of the inside, There's my chain rule. And now if I want to use my result from part A, and I want to find the second derivative, again, I start to do this. I get overexcited. I probably wrote that too big. Do you see that it would be a product rule with a chain rule embedded? So what does our product rule say? Keep one the same. That's keeping the first one the same. Multiply by the derivative of the second one. This is where life was easy so far. Plus, keep the second one the same. Multiply by the derivative of the first one. Well, now my 2 would come out in front. 6, keep the inside the same. Subtract 1 from the exponent 1, multiply by the derivative of the inside. And there we have an unsimplified answer for this one. Okay? If you wanted to factor this, you could. Can you see that this one could be factored? What do you have in common between these two terms? This is term 1, all connected by multiplication. This is term 2, all connected by multiplication. I have an x squared minus 3x. I also have 3 times 2, 6, and 6. I could factor that out as well. So this is what's in common, square bracket. Now what's left in this one? Just an x squared minus 3x. In this one, a 2x minus 3 squared. If you wanted to find the third derivative from here, you could think of it as a product rule this way. Or you could have done the third derivative from this one, in which case this would just be a chain rule by itself. And when you did this part, you would have to do a product rule inside of a product rule. So our second and third derivatives are getting complicated. Okay? We could have also just taken the same question and said, I would like to take the time to multiply this out. If I take the time to multiply this out, does it make sense that, okay, you could write it out. Option 1 for multiplying it out. How many of you would do this option? Multiply 2 of them first. We're going to get minus 3x cubed minus 6x cubed plus 9x squared. And then do all of your arrows here, and you would get an x to the 6. This is a minus sign. We're going to get minus 3x to the 5 minus another 6x to the 5s. I don't like that number. Am I doing something? No. Minus 9. Here we go. This would be minus 6x to the 5s. 6 and 3. Okay. Yeah, 6 and 3. I don't know where I got the wrong number. 9. I like that number better. Minus 9x to the 5s. How many x to the 4s will we have? 9 here. 18 there. Right? Plus 27x to the 4s. How many x to the 3s will we have? Just these ones. Agreed? That would be one way to multiply it out. Or you could use Pascal's triangle. So Pascal's triangle, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. You have an exponent of 3. So reviewing Pascal's triangle, your coefficients would be the 1, 3, 3, 1. First term is an x squared. You'd have your x squared 3 times. Then you would have your x squared twice. Then your x squared once. Your second term is a minus 3x. You would start with none of them, have one of them, have two of them, and then have 3 of them. This is the binomial theorem, which you will get in grade 12. Using the binomial theorem, simplifying each of these, this gives me my x to the 6. Here I have my minus 9x to the 5. Here I'm going to have negative 3 squared is 9 times 3 plus 27 x to the 4, and negative 3 cubed minus 27 x cubed. Both of them take a little bit of effort to expand. What is the advantage of expanding them? No chain rule, and my derivative, so I'm starting with 6x to the 5 minus 45 x to the 4 plus, what is that, 108 x cubed minus 81 x squared. My first derivative has some multiplying to do, obviously, but not too crazy. And then my second derivative, 30x to the 4 minus 180x cubed plus 324x squared minus 162x. And in this form, we can see eventually, at a certain derivative, everything will be 0. Because the powers are going down. The next derivative, you'd be left with a minus 162. And after that one would be 0. If we had continued along the path of this for derivatives, it just gets bigger, and like chain rule and product rule just expands. And you could keep going. And you'd actually be able to, like, you could see in the other one by like for sure the 10th derivative, everything would be 0. If you kept going on this, you would still have x's on your 10th derivative, which everything would, if you put it together and simplified it, would equal 0. You just wouldn't recognize it. We could come up with some very complicated formulas equal to 0, which I don't know what the point would be, but we could. Okay, so we have, if you're doing multiple derivatives, there's some advantages to simplifying first. The disadvantages to simplifying first is you have to do more work at the beginning. So it's a give and take that way. All right, so that's all we're doing on second and third derivatives because it's really nothing new.